Hello guys, hope you all are doing well. We were solving the previous year questions of GATE Chemical Engineering, and we have completed 1990, 1991, 1992, and section A of 1993. Today we will see some practice questions which will enhance our preparation, and the topic is thermodynamics, specifically the chapters are thermodynamic properties, and some questions are from solution thermodynamics. So without wasting time, we'll look into the questions. So question 1, practice question 1 is, an ideal gas mixture contains 5.6 liter of oxygen and 16.8 liter of hydrogen at normal temperature and pressure. Calculate the increase in the entropy. Okay. So we have to find increase in the entropy after mixing. So entropy of mixing of an ideal gas, sorry, this is of an ideal gas is given by delta S mixing is equal to minus NR mole fraction into Ln mole fraction of component, where I from 1 to n. Okay, so there could be one component, two component, three component. One component will be not be there. Two component, three component, four component. Okay, now calculating mole fractions of O2 and N2. We require mole fraction. Okay, O2 and N2. So at NTP, volume of a gas is occupied by, at NTP, this is the volume of gas. Okay, this is the volume of gas. 22.4. This is liter per mole. If you want to convert it meter cube per mole, then meter cube per kilomole. Okay, this meter cube into K will become liter per mole, right? Because liter is equal to meter cube by 1000, and 1000 is K, right? So both are same. So since O2 and N2 given in liters, okay, O2 and H2 given in liters, so we will calculate the mole fractions. So moles of O2 will be 0.25 moles. Moles of N2 will be 0.75 moles. What will be the mole fraction? The same, right? Given moles upon total moles. So entropy of mixing will come minus NR, putting all the values in equation 1. This is equation 1. Minus 1 mole, and mole will cancel out. Okay. Putting all the values, we'll get 4.675 joule per Kelvin. Okay. So this is very straightforward question, and since it is small, and it might get asked for 1 mark, but we have to remember this delta S of mix. Okay. Okay. Going to the next question. Estimate the fugacity of isobutane at 15 atm and 87 degrees Celsius using the compressibility factor. So fugacity, we know that it measures the deviation from the ideality in the vapor phase. Okay, that is called fugacity coefficient. Okay, we have Borel equation of state Z is equal to 1 plus dP upon RT, where given second Borel coefficient is this. Okay, so estimate the fugacity of isobutane at 15 atm and 87 degrees Celsius. Fugacity coefficient from compressibility coefficient. This equation is very important, and no book will provide this equation after joining every formula. I have formulated this equation. You can take two at a time. Either you can take this equal to this, this equal to this, this equal to this, this equal to this, this equal to this. In 2015, GATE has asked on the basis of this formula. Okay. So this is complete formula. Okay. GR upon RT is equal to ln phi is equal to summation of xi ln phi I, where phi I is the partial activity coefficients, partial fugacity coefficients. Ln f by p is equal to 0 by p, z minus 1 by p dp in 0 by, where z minus 1 is called 0 by p vr upon rt equal to dp. So we will take this to find the fugacity coefficient. Okay, now putting viral equation of state in this form. How? Like this. Z minus 1, we just took, just interchange Z minus 1 by P is equal to V upon RT. Putting this V upon RT in value of Z minus 1 by P. So we will get this equation. Now we will get this straightforward. This. Okay. Now putting all the values. So meter cube and meter will cancel out, kilopascal and kilopascal cancel out, Kelvin will cancel out, mole and mole will cancel out, this K remains. So this is 1000, so I will multiply this here 1000. Okay, so after calculating you will get F is equal to 14.99. Okay, ATM. Okay, so this is also just if you know the concept and the basics, you can find out. But that equation that I have provided you, this equation is very important. This whole equation. So just write it somewhere. Okay. So going to the next question. The partial molar volume of water component 1 in its mixture with methanol component 2 at 25 degrees Celsius and 1 atm pressure can be approximated by V1 bar, partial molar volume of water, 18.1 plus AX2 square, where A is equal to minus 3.2 centimeter cube per mole. Develop an expression for partial molar volume of methanol at the same condition given that V2 at 25 degrees Celsius and 1 atm is 40.7 centimeter cube per mole. Determine also the partial molar volume of methanol at infinite dilution. Okay. So we have to calculate the partial molar volume of methanol very first. Applying Gibbs-Duhem equation. So we know that there are 6 Gibbs-Duhem equation. Okay. Gibbs-Duhem equation. If we when you will go through the fundamental properties of thermodynamics, then you will find out these equations. Okay, so we will use one of those equation here today. So for partial molar volume of two component system, we have this equation: x1 dm1 by dx1, x2 dm2 by dx2, where m1 and m2 are the fundamental properties. So replacing m1 and m2 with volume. Okay, now putting value of v1 here, we have given with v1, so I just put the value v1 here, this. Okay, and now differentiating it. So after getting differentiate this equation above one, see, very first I converted this d x1 is here. I will write x1 is x1 plus x2 is equal to 0. We know that summation of mole fraction is always, sorry, not 0, 1. Summation of mole fraction is equal to 1. So if I dx1 plus dx2 differentiate this equation is equal to, it will give 0. So dx1 is equal to minus dx2. So very first step, I just replace this x1 with minus dx2. So this minus will come here and dx2 will be here. Differentiating, this will be constant, so here 0, a will be constant, comes out. So d upon dx2, x2 square will remain in the equation, is equal to, this side will remain same. Okay, this side will remain same. Now we will get, after solving this equation. Okay, now x2 and x2 will cancel out. Okay, cancel out. Now I just took this x2 dx2 from here to here. Okay, now what I did in this step, this is dx2, I again replace this with minus dx1, so the minus sign will become plus here. Okay, now integrating, this step is important. Why? To understand. See, this is dx1, this is dv2 bar, this is partial. When x1 will 0, either we have x1 plus x2, okay, equal to 1. When x1 will be 0, that means there is no first component in the solution. That means the whole solution become v2. When x1 equal to 1, there will be partial volumes. Component 1 as well, component 2 as well. Okay, so this need to be understood. Now solving equation, we will get V2 as this. This is simple integration. When you solve this, you will get this. Okay, and this V2 we have given in the question. V2 is equal to 40.7. If you will see the question, this is V2 we have given 40.7. Okay. Now, second thing, you have to calculate the infinite dilution, right? So at infinite dilution, V2 infinite will be this. How? From this equation, always remember dV2 bar infinite. At infinity, if I want to calculate infinite component, infinite of a component 2, at infinite dilution of a component 2, that means x2 will become 0 because we have diluted it infinitely. So it becomes 0 and x1 is equal to 1. Same concept I applied here. So x2 is not there. So x1 will become 1. So 40.7 plus a, and a is minus 3.2. So you'll get this. So this is the complete solution. And this question is very important. The main thing which is important, you have to remember this equation. These two equations. Okay. And remember, this will be replaced by Gibbs free energy, Helmholtz free energy, anything you have to find out. Okay. Now, going to the next question. This is the thing. This is the thing. Okay. Now, going to the next question. This practice question 4 is for practice. Okay, this is same as we have find out the fugacity. F by P, ln F by P is equal to e की power Bp by RT. Finally, it will come, but you have to make some modification, that PV minus PV minus PB is equal to RT. We have the given value of B. Okay, then you will make it Z. How? RT divide, then this is Z minus PV upon RT is equal to 1. Okay, so these kind of thing modification you have to do and then apply same equation. You will get the answer. Okay, so this is for your practice. Now, this question is very important, because when you will see this question, the beauty of the question is, very first it is from the chemical thermodynamics, from the excess Gibbs free energy, and this question is from the azeotropic composition. And we know that at azeotropic composition, vapor composition and liquid compositions remain the same. So we'll see this question. This question is very important. Okay, so for a binary system, the excess Gibbs free energy of A and B at 30 degrees Celsius is given by G excess upon RT and 0.625 x1 x2. Very first, when the original expression, standard expression is A x1 x2. When this standard expression is given, the automatically ln gamma 1 is equal to A x2 square and ln gamma 2 is equal to A x1 square automatically. Okay, where gamma is the activity coefficient. The vapor pressure of component 1 and 2 are given by, we have vapor pressure, we have to calculate from these formulas. Calculate the composition is at azeotrope. Okay, so we have to find the composition at azeotrope. Applying modified Rolle's law, what it said, phi1 y1 pt is equal to x1 gamma 1 p1 set, where this is fugacity coefficient, composition in vapor phase of a component 1, total pressure, composition of component 1 in liquid phase, activity coefficient, P1 set is the vapor pressure. So fugacity coefficient measures the deviation from the ideality in the vapor phase. Activity coefficient measures the deviation from the uh, sorry. Fugacity coefficient measures the deviation from the ideality in the vapor phase, and activity coefficient measures the deviation from the ideality in the liquid phase. Okay. Now for component 2, the same. Okay. At azeotrope x equal to y, then when x equal to y means the y1 and x1 will cut out, y2 and x2 will cut out. So the remaining thing is this. For component 1, pt is equal to and pt equal to n. In most of the cases, phi1 is equal to phi2. Okay, this always remains same in most of the cases. So we have left with these two equations, right? Now, taking log on both sides. With the first equation, first component ln pt is equal to ln gamma 1 ln p1 set. This is the property of log. Similarly, for component 2, equating 1 and 2, we will get this. Okay, just rearranging. For this model, GE upon RT 0.625 x1 x2, that is ax1 x2. That means ln gamma 1 equal to ax2, as I said, ax2 square, and ln gamma 2 become ax1 square. There I made a mistake, I think. No, fine. Okay, so putting these value in 3, ln gamma 1 and ln gamma 2 we have, put these value here. Okay, so we'll get this. I just replaced x2y 1 minus x1 and square is there. After calculating, just simple mathematics, this will come out. X1 will be 0.26. So see, at the initial x and y cut out from both the equation, and we have to find the value of x1. So this is the beauty of the question. You will got stuck when you will see that at azeotrope x is equal to y. So that thing will cut out. So how we will calculate the composition? So this question is very important. Okay, so if you have any doubt, any kind of thing, just comment it below. I'll try to reply as soon as possible. And if you have not yet subscribed to my new channel from where I upload all the solutions of chemical engineering, if just the bricks scale search on YouTube, you will get the solution. And for 1990 to 1991, type on YouTube, search on YouTube Kelly IITG, you will get all solutions. Okay, so please like and share, subscribe guys, it is a humble request. If you feel okay, and if you don't want to subscribe, that is totally fine, but my lecture will be open for all. Okay, so bye guys, take care of your parents as well.